In section 2.3, now we are solving trigonometric equations, and this begins very similarly to solving equations in algebra. So we're going to be using many of our algebraic techniques. We're going to try to get all the like terms together. Maybe we'll try to factor, ultimately isolating the trig function on one side of the equation. So here we're trying to solve for x, but x is inside of a sine function, the input of a sine function. So first thing we're going to do is get the sine by itself. This one is multiplied by 2, so we need to undo this multiplication by 2, and we'll do that using division, so dividing both the right side and the left side of the equation by 2. So on the left side, the 2's cancel, and I'm just left with sine x. On the right side, I'm going to leave this as a fraction, 1 over 2. Now, we have to figure out for what x values is sine equal to 1/2. Two ways that you could do this. You could use the inverse to undo a sine. So we could take sine inverse on both sides. Or you may know what angles would give you a sine value of 1/2. We could check this on our unit circle. This is a positive 1/2. Remember, sine is our y-coordinate, so we're looking for the y-coordinate to be a positive 1/2. We've got one there, and we should have one second quadrant there. Okay, so that's at pi over 6 and 5 pi over 6. But as we go around the circle and these values start to repeat, we're going to get sine values of 1/2 again, over and over and over infinitely. So in order to represent all of these solutions, we call this the general solution. We just need to add multiples of the period, and the period for sine is 2 pi. So here's what we're going to do. We know that this x value, and here I'm just using my knowledge of sine values for the special angles. If you're using the inverse, you would end up with x equals sine inverse of 1/2, and then you would still need to evaluate the sine inverse to get pi over 6 and 5 pi over 6. And then to generalize this solution, we're just going to add multiples of 2 pi, since 2 pi is the period. So we just add a little plus 2 pi times n. And I'm using n to just represent any integer. And I'll do the same thing with 5 pi over 6. Add 2 pi times n. So these two together gives us our general solution to this equation. And the good thing about solving equations is that you can check if I were to plug pi over 6 in for x, my equation should hold true. And the same thing is true for 5 pi over 6 and all of their coterminals. Next, we'll move on to some quadratic type equations. So if you remember solving quadratic equations in pre-calculus algebra, there were 4 methods. Sometimes you could just use the square root. Other times you would factor. Sometimes we did completing the square to make it so that we could factor and use the square root. And then the 4th method was quadratic formula. We can do all of these things with the trig function. So if your trig function is square, you may need one of these methods in order to isolate it. In this example, looks a little bit complicated. There's a lot going on. We have 2 different functions. So it's going to be hard to combine them using addition or subtraction. So I may want to try to rewrite them as multiplication or as factors so that I can split them up. So first step, if I want to try to factor, I'm going to put everything on one side. A factoring method works only if one side of the equation is 0. So I'm going to put everything on one side so that I have a 0 on one side of the equation. And I'm just going to do that by subtracting the whole right side. With this right side, so I'm just going to subtract 2 cotangent x from both sides. Now, what I had on the left side is not going to be like terms with the 2 cotangent x. So I'm just going to kind of add it on here that I'm subtracting to cotangent x. Right side is now 0. Now I want to see if I can factor the left side. So first thing with factoring, I want to check for a greatest common factor. And I'm looking between my terms. So remember, terms are separated by addition and subtraction. So all of this is one term, and all of this is the second term. And I'm looking for factors that the terms have in common. And here between these two, I see that they both have a cotangent x. So greatest common factor here is cotangent x. Let's factor it out. If I divide out the cotangent x from the first term, what's left over would just be the cosine squared. And from the second term, if I divide out the cotangent x, all I would have left here is a 2. Now I want to double check. If I multiply that back together, do I get where I came from in the last step? Remember, if you can't, you may have done something wrong. But here, if I distribute the cotangent x, I do get the previous step, so looks good. Now I have it written as a product. Something multiplied by something else. If the right side is 0, I can set each of these equal to 0. So cotangent x times that whole parentheses gives me 0. Then it has to be true that cotangent x is equal to 0 or cosine x minus 2, that's everything that was in parentheses, is equal to 0. Okay, so if the product of these things is 0, one or both of the factors has to be 0. That's the reason we can split that up. Okay, so now we got two little equations and we're going to solve them individually. So cotangent of x being equal to 0, I need to find the x value, the angle that would give me 0. If I took cotangent of that angle, I get 0. You find this the way that's most comfortable to you. The way that comes to mind for me is that cotangent is the reciprocal of tangent. So if I want cotangent to be 0 over something, that means that tangent would have to be something over 0. Something over 0 is undefined. So in my circle, I'm looking for places where tangent is undefined, where the denominator would be 0, tangent sine over cosine, so cosine would have to be 0. I want to find that on my unit circle or my chart. We need cosine to be 0. Cosine is my x coordinate, so that is going to happen. And it also happens again down here, but because the period of tangent and cotangent is pi, it's going to happen every time I add or subtract pi to pi over 2. So here, if I were to write my solution as pi over 2 plus n pi, that's going to include 3 pi over 2. So we don't necessarily need to list them separately. All right, so cotangent is 0 at pi over 2. And I'm adding multiples of pi. So not using 2 pi this time because it's cotangent, and the period for cotangent is just pi. Okay, so for the other equation, I need to get this cosine by itself if I'm going to solve this. So I'm going to add 2 to both sides, and I get that cosine squared is equal to 2. Okay, so I want to isolate cosine, so I'm going to undo that square. We're going to use square root to undo the square. So I'm taking the square root on both sides. And anytime you introduce the square root, we have to be concerned about the positive or the negative. Is it positive or is it negative? Because we don't know what this angle is. So we don't know what quadrant we're in. Could be either one. Okay, so I'm looking for cosine to be a positive or negative square root of 2. Square root of 2 is actually bigger than 1. So cosine never even reaches that value. So this equation has no solution. Cosine x equal plus or minus square root of 2 has no solution. So no x value that would make that true. So our only solution here is x equals pi over 2 plus n pi. Right, so another quadratic type. There's one in the slides that's a straightforward factoring, and you can read that one there. And of course, ask me if you have questions about it. I'm going to do one that has one extra step, so just a little bit more complicated, so that you can see how that works. What's extra here in the instructions is that they're giving us an interval, so we're not looking for a general solution. We don't have to add that to pi n or pi n. We're just going to find the solutions that are between 0 and 2 pi, and we're going to stop there. So I've got the square here, so I know this is a quadratic type, but I also have two different functions. I've got sine and cosine, and I want to see if I can make it just one function here. Because I've got everything on one side, but I can't factor it the same way that I did the last example. There's no greatest common factor here. So I want to see if I can do something else to rewrite this so that it's only sines or only cosines. So that's going to require an identity. And I do have identities that involve sine and cosine. So I'm going to try to take this sine squared, and I'm going to use the Pythagorean identity that says sine squared x plus cosine squared x equals 1. And we have a few times now rearranged that. And sine squared is equivalent to 1 minus cosine squared. So if you rearrange that equation a little bit, subtracting the cosine squared from both sides, you get sine squared equals 1 minus cosine squared. Right? And so in our problem, we have a sine square, and I'm going to replace it with 1 minus cosine squared. So I'm rewriting this, but replacing the sine square with 1 minus cosine squared, the whole thing. Okay. Okay, so now at least I don't have sines and cosines anymore. I still have the square, but they're all cosines. So I'm going to get rid of the parentheses by distributing this 2. So 2 times 1 gives me 2, and then 2 times negative cosine squared is negative 2 cosine squared. Now let's see how much we can simplify that. We do have like terms, the constants here, the 2 and the minus 3. If I add them together, I would get negative 1. Combining these two, I get negative 1, still equal to 0. Okay, so now I have something that looks like a quadratic equation, and I want to try to factor it. Now, and you can factor it from here, but it's much easier, in my opinion, to factor if your leading coefficient is positive. So I don't want this negative 2, I want to make it positive. And you can change all the signs by either multiplying or dividing everything, as long as you do every term on both sides by negative 1. So I'm going to multiply everything by negative 1, and that's going to change all of the signs to opposite whatever they were. So this will be a positive 2, a negative 3, a positive 1, and 0 times negative 1 is still 0. So you can achieve this by either multiplying or dividing everything by negative 1. Okay, so now it looks easier to factor to me. If the cosines throw you off, just rewrite it with x's and think, how would you factor something like this? Lots of different ways to do it, and go ahead and stick with whatever you're used to from algebra. The way that I like to show, if you're starting from scratch and you don't have, a way that you've been practicing, is to use the AC method, because it always works, and it's not, there's no magic tricks to remember, in my opinion. So remembering that this is A, this is B, this is C, the coefficients in front of your x's. The AC method uses A times C, so A times C, and this problem is 2 times 1, which is just 2. So then you need factors of 2. So numbers that multiply to 2, that add up to negative 3. Okay. So I want them to multiply to 2, so the signs have to be the same. So they could both be positive, or they could both be negative. And since I want them to add up to negative 3, they gotta be negative. So I'm going to write out all the ways that I can get 2. So I can multiply 2 times 1, which is the same as 1 times 2, or negative 2 times negative 1. Okay. Take a moment to convince yourself that both of these multiply to give me positive 2. And if you have a favorite factoring method, go ahead and you don't need this part, just putting this here in case we're struggling with factoring. Help with that. Okay, so next step would be to split the middle. So you're going to rewrite your middle term using these two numbers that you found. So 2x squared, I'm not changing that. But I'm going to rewrite the 3x as negative 2x minus 1x plus 1. Okay, so this part here is still negative 3x, and I split it up using these numbers that I decided on from a times t. Next step is to factor by grouping. So you're going to group any way you want to, and you're going to take out the greatest common factor. So from these first two terms, they definitely have a 2 in common. They also both have an x. So greatest common factor is 2x. In the second two terms, they don't really look like they have anything in common. So remember that 1 is always a common factor, so we can use 1. And since that x is negative, I'm going to make it a negative 1. If I factor out a negative 1, what's left over would be a positive x, and then this would have to be negative 1. You can always double check, multiply it back together, make sure it's equivalent. But this method works if you get the same thing in parentheses. It becomes the greatest common factor. So if you factor that out, what's left over is just the stuff on the outside. So the 2x and the minus 1. And this is your factor. So first time seems like a lot. As you practice it over and over and over, it gets a bit easier. An alternative to doing this factoring is just to use the quadratic formula. You would still use this a, b, and c and put them in the quadratic formula. That also works. Okay, so we're going to do cosine x minus 1 times 2 cosine x minus 1 equals 0. So now it's written in factored form. I got two factors. Multiply together to give me 0, so I can split them up. Cosine x minus 1 is 0, or 2 cosine x minus 1 equals 0, or they both equal 0. And I'm going to solve these equations individually to get my solutions. So looking at this left one first, to isolate the cosine, I just need to add the 1 on both sides. So I got cosine x equals 1, and I'm going to head to my circle to find where does cosine equal 1. Cosine is the x coordinate, so it only equals 1 right here. So now I need to decide, is that angle 0 or is it too high? And based on the interval that they gave me, so notice here that the bracket on the left side means 0 is included. Parentheses on the 2 pi means it is not included. So since 0 is included, I want 0 for that. So this is going to be x equals 0. Included because of the bracket. All right, and so I'm not going to add multiples of 2 pi because that would give me angles that are not in the interval that I was given in the instructions. All right, so let's solve the second equation here. I'm trying to isolate the cosine. So we're going to add 1. And then we need to undo this multiplication by 2. So we're dividing this by 2. And now we're looking for where does cosine equal 1/2. Cosine is my x coordinate. Yes, x coordinate. And I'm going to look just on one trip around the circle between 0 and 2 pi. So cosine is 1/2 right there. And it is 1/2 again down here. And because they gave me the interval, just those two are my solutions. So pi over 3 and 5 pi over 3. All right, so final solution here is x equals 0, x equals pi over 3, and x equals 5 pi over 3.